So today we're going to talk about number sets. We're going to describe all of the number sets, and then we're just going to differentiate between rational and irrational, just kind of as a review. So look at the front side of this worksheet. So let's define natural numbers. Does anybody know what natural numbers are? 1, 2, 3, the counting numbers. So this would be 1, 2, 3, 4, and so on. Okay? Well, and a lot of times we get lazy and we don't want to write the word natural numbers, so we use a symbol. The symbol for natural numbers is an N with a double line on the left side. Okay? So we move on to whole numbers. What are whole numbers? It's the natural numbers, but it starts with 0 this time. So 0, 1, 2, 3, and so on. No, negative numbers do not work for whole numbers. They start with 0. And the symbol for whole numbers is a W with a double line on the left. Now we move on to integers. What are integers? What's that? It's the whole numbers and the negative version of the whole numbers. So natural and whole numbers have a beginning number and then they just go to infinity, but integers go to infinity on both ends. So we would start with a ... -2, -1, 0, 1, 2, ... And if you look at the list, you notice there are two sets that both start with I. So we have to come up with something other than I. So it's going to be Z. Don't ask. I don't know. Math people don't make any sense. So we draw a Z with a double line down the diagonal. Okay? Now, it's important to note, which number set does 4 belong to? All 3, right? Well, if you are in set N, you're automatically in set W, and you're automatically in set Z. If I told you that a number was a whole number, can you guarantee that it's a natural number? No, why not? There's a 0, so if that number happened to be 0, then it doesn't belong to N. If I told you that a number was in Z, is it guaranteed to be in the other two sets? No. But it does work the other way. If a number is in N, is it also in W and Z? Yes. So as we go down the progression, all of these belong to that, and all of these belong to this. Well, there's one more set that we can include where these all fall into, and it's called the rational numbers. And defining the rational numbers is a lot harder than the other 3 sets. The simple definition for rational numbers is fractions. But when I say fractions, I don't mean every fraction, because there are some fractions that don't fit in the rational number set. I mean fractions where the top number is an integer and the bottom number is an integer. So if we move on to irrationals, we would write non-fractions. But that's not the only definition, and in fact, that's not really very useful. Can you think of an irrational number? What's the most famous irrational number? Pi. So irrational numbers would be numbers like pi. What about pi over 3? Rational or irrational? Irrational, but wait a minute, it's a fraction. Right. When I say fractions, I mean numbers where the top is an integer and the bottom is an integer. So this is not really considered a true fraction because the top is already irrational. So other than fractions, the way to define this is to look at decimals. There are two types of decimals that are rational. Yes, Joseph? Right. So these fit inside there, and these fit inside there, and these fit inside there. Is that what you're asking? Say that again, sorry. Right. Or sometimes they don't even have a denominator. It's just a number without a denominator, and that number is irrational. But yeah, you're right. Okay, so when we look at the decimal of rational numbers, we look for two things. First, we check to see, does the decimal stop? So decimals stop, or there's another thing. What I mean by that is, if you're writing out a decimal and you run out of numbers to write, it's rational. For instance, the number 5. Rational or irrational? Rational. It can be written as a fraction. What is the fraction for 5? 5 over 1. Okay? Well, 5.3, that decimal stops. So, can you turn 5.3 into a fraction? Yes. It would be 5 plus 3 over 10. And maybe I should get rid of the 5. Let's just do 0.3. 0.3. What is this as a fraction? 3 over 10. What if I add another number? 37 over 100. What if I added another number? 371 over 1,000. So as long as it stops, I can write a fraction. Okay? But sometimes there are fractions that go on forever. The decimals go on forever, and they're still rational. Can you think of any? Non-repeating. Repeating. So if I did 1 divided by 3, what's that as a decimal? It's 0.33333. That's going to go on forever, right? But it's the same number over and over and over. So we call that repeating, so the decimals stop or repeat. That makes sense? Now, this is just kind of a little trick that I'm going to show you. If you have a repeating decimal and you want to write it as a fraction, you just take the repeat number and you divide it by 9. So this is 3 over 9. 0.1 repeating is really just 1 over 9. That's just how it works. I don't know why. It just does. I don't know. Right, well, what I meant was this. And even if you have a multiple repeat, go ahead. Good. So 7, 3 repeating. So the fraction for this is 73. Anyone want to guess? Over 99. Thank you, Jordan. This is tomorrow's assignment for whoever, somebody wanted it. So it would be 99. Well, 730 wouldn't work because it ends in a 0. But if we had 731, then it would be 731 over 999. Well, if it's a 0, we don't write it, right? 0.30 is really just 0.3. Yeah, so if it ends in a 0, we just drop it. The trouble you get into is sometimes they don't begin with a repeat, like 0.462183, and only this much repeats. And there is a way to put it over 9999999, but it's not as easy as it looks. You have to really do a little bit of math and mix it up and then make it work. But there is a way to make this into a fraction. It's just not easy to do. It's not easy like this is. Okay? So, when we talk about repeats, you can have one number repeat. You can have multiple numbers repeat. You can even have non-repeat and then end with a repeat. And in all cases, those numbers are rational and they can be written as fractions. Okay? So we move on to irrational, which we have as non-fractions. Oh, and the rational number, see how we have two r's? And real numbers is r. So for rational numbers, another way, so rational uses division, right? 1 divide 5. And the answer to a division problem is called a quotient. So the symbol for rational is a Q with a double line. And just remember, it means quotient, which is the answer to a division problem. Okay, so irrational is a non-fraction, which doesn't help us a lot, because really we need to look at the decimal. So for irrational numbers, the decimal never stops and never repeats. Is that possible? How can you go on forever and never use the same numbers? Ah, good. In the same order. That's the trick. If you look up at my pi on the wall, do I use 2 lots of times? Yes. But is there a set of numbers that repeats over and over to infinity? No. It's just random. I mean, you don't ever know. So, that number is irrational. The trouble is, most of the time, you cannot tell it's irrational by looking at the decimal. Okay? You can look at the decimal and see if it's rational, but you can't always look at the decimal and see if it's irrational. And I'll show you what I mean here in a little bit. So, there are some famous irrational numbers that we'll talk about in a minute. What are real numbers? Real numbers are all Q and, irrational, the symbol is an I. Q and I. Now, inside Q, we also have Z and W and N. But I don't need to list Z, W, and N because Q contains all of those. So if you look at a number line, and you throw a dart and hit the number line, the number you hit is either rational or irrational. One or the other. Now, if it's rational, it might also be an integer or a whole number or a natural number. But today we're just going to distinguish between, is it rational, can it be written as a fraction, or not. It's that easy. What's the symbol for real numbers? The R with a double line. And what are complex numbers? Also known as imaginary numbers. So they have numbers with i's in them. So complex numbers are the square root of negative numbers. That's where the I comes in. And the symbol for complex numbers, it's a C with a double line on the left. Okay. So let's consider the number 1 divides 7. This is a little tricky. What do they do? So in my calculator, I'm going to type in 1 divides 7. Is that number rational or is it irrational? Well, does the decimal stop? Can I be sure? Could 9 be the last one? Your calculator only has 10 digits or 11 or something, I don't remember. But once it runs out of digits, the calculator just quits putting them. So Is there any way to tell that 9 is the last number? No. I don't know. There's no way to tell. Well, I know, but you don't know yet. So, I'm not sure about that. What about, does it repeat? Do you see a pattern in there? We almost see one, right? Yeah. What's that? I have a phone call. So if you look at the pattern, 1, 4, 2, 8, 5, 7, and then I start over 1, 4, 2. Oh, wait, it doesn't work. Or does it? Joseph? Right, maybe it's actually 8, 5, but since it couldn't put the 5, the calculator decided to round the 8, which would turn into a 9. Can we be sure? Well, you can't yet, but I can. I know this is rational. And I knew it was rational before I even plugged it in my calculator. How come? It's a fraction. 1 over 7 is an integer divided by an integer, so it's rational. I also know another trick you guys don't know. If you have a division problem, the number of decimals that you're going to get will be less than or equal to the number you're dividing by. So I'm dividing by 7, right? Either this number is going to stop having decimals after 7 decimals, or it's going to repeat after 7 decimals. It can't go bigger than that. Does that make sense? So if I count here, 1, 2, 3, 4, 5, 6. So this one has to repeat. And so the 1s match, the 4s matches, the 2s match. And this was an 8, but it got rounded up to a 9. So what I'm pointing out here is your calculator is very unreliable. If you plug a number into your calculator to see if it's irrational, most of the time you won't be able to tell. If it stops, that works. If you see a repeat, it works. But if you don't see a pattern, does that tell you it's irrational? No. Okay, so you have to be wary about using your calculator, because it doesn't always tell you what you need to know. All right, so come down here. What are some examples of rational numbers? I'll give you one. -2, rational. Can you think of any others? 1, 5, any integer. What about 3/5? Rational. If I have a decimal, 4.8621, and I stop, that's rational. How do I know that stops and it doesn't keep going? There are no dots on it. Is your calculator going to show you the dots? No. That's why you don't trust your calculator. Okay? What about 465.2781? Rational or irrational? Does it repeat? Yeah, 781, 781. We would assume it would continue 781, 781, 781. Okay? So that would be rational. What are some examples of irrational numbers? Well, let's put our favorite one up there. Pi. That's irrational. Okay? What are some others? Ooh, careful. If the top is actually rational and the bottom is rational, it still works. So 2.7 over 8.6, that's still rational. That would still be rational. If the top is rational and the bottom is rational, then the fraction is rational. That would 2.7 is 2.7 repeating would be rational. The only time a fraction stops being rational is if you do like irrational over 4. That would be irrational. Okay. There's another number that you'll run into, the number e. You haven't seen this yet, probably. Right here. The number e is 2.718281882. Does that repeat? 182281882. No, it doesn't. It kind of looks like there's a pattern, but there's not. E is a number that's used in calculus a lot, and it's called the exponential number, and you'll see it probably this year, later on. But you haven't seen it yet. Also, anytime you take a square root and it doesn't come out to be a whole number, like the square root of 7. Here is the one time you can trust your calculator for irrational numbers. If I do square root of 7, I'm telling you that this is guaranteed to be irrational. What square roots would not be irrational? Square root of 9. So if I type in square root of 9 or any other perfect square, that would belong in this list. So if I had a square root of a big number that I didn't actually know the perfect squares, just because that came out with some decimal, I can guarantee that it goes on forever and never repeats. Okay? Hang on a second. Let me show you another really strange irrational number. So let's do 0.001, 0.12, 0.123, 0.1234. Rational or irrational? But there's a pattern. It's not repeating. The pattern's getting bigger every time. So this pattern will continue forever. Will there be one set of numbers that happens forever? No. So something like that, just because it has a pattern does not mean rational. The pattern actually grows, and that would be irrational. What if the pattern shrunk? What if I add 0.987654321, 8765431, 7654321? Rational or irrational? Why irrational? Does it go on forever? Eventually it's going to stop. Eventually I'm going to run out of the pattern and I don't have any more numbers. So if it stops, it belongs to rational. If the pattern lengthens every time, that would be irrational. But even if you have a huge pattern and it's slowly getting shorter, eventually it's going to run out. So that would be rational. Okay. Turn the page. I'll do a couple of these with you. Number 1. Rational or irrational? Rational, how come? So I'm going to put this in the set Q. Now, remember, with fractions, you don't want to use your calculator. So if I do 4, 5, 7, 8, 9 and divide it by that denominator, the bottom number is 78,000. This one either repeats or it terminates, but I might have 78,000 decimals before I figure that out, whether it repeats or terminates. Yeah. That's just a coincidence. The fact that it's a fraction makes it rational. Even if you can't find a pattern like that, it would still be rational. Yeah. Okay, number 2. Does number 2 go on forever? It stops. How do I know that? There's no dot, dot, dot. So if it stops, it's automatically rational. Okay? Number 3, rational or irrational? How come? Can you guarantee? Okay, it goes on forever. And do we know it doesn't repeat? Can you guarantee that's never going to repeat? No, we don't know. So just because it goes on forever, we can't tell if it's rational or irrational. So this one would be unknown. We're not sure. So I want to have you go all the way to 24, but I want to answer these questions. So in higher mathematics, we study something called closure, which means if I take one number from a particular set and another number from that same set, and I add them together or I multiply them together, do I get a number that is still in that set? So if I take rational and add it to rational, do I still get rational? And that's called being closed. Am I guaranteed to get a rational number? So if you take a number with a decimal that stops and I add it to a number with a decimal that stops, what do I get? A number with a decimal that stops. If I take a stopping decimal and a repeating decimal and add them together, what do I get? A repeating decimal. If I add 2 repeating decimals, what do I get? So if I had like 0.11111 plus 0.222222, what's my new repeat? 0.3s forever. So what kind of number do you get when you add 2 rational? Every time you get a rational. It always works. Okay? So for 26, what happens when you add 2 irrational numbers? Well, pi plus pi equals, try again, 2 pi. Is that rational or irrational? Irrational. Okay, if I had a decimal that's irrational and another decimal that's irrational, is there a case in which I could create a number that has a stopping decimal using addition or subtraction? Is there any way to get rid of all of those decimals using addition or subtraction? How would you do it using subtraction? You could get 0. What if these 2 numbers are exactly the same and I subtract? So what about pi minus pi? Is 0 rational or irrational? Rational. So the answer here is you either get a Q or you get an I. Okay. Now, if I take a fraction and I multiply it by a fraction, am I guaranteed to get a fraction? Yeah. A fraction times a fraction is always a fraction. So this one would be rational. If I take an irrational number and multiply it by an irrational number, do I always get an irrational number? Well, certainly pi times pi is pi squared, which is irrational. So you can get irrational. But can I take pi and multiply it by something and get rid of the pi? How do you cancel a number using multiplication? No, negative pi would be addition. How do we do the opposite of multiplication? Divide. So if I times this by 1 over pi, what's my answer? 1. So this is either Q or I. Okay. So what if I add a rational and an irrational? If I take a stopped decimal and multiply it by an irrational, or add it to an irrational decimal, my new decimal will be irrational. What if I take a repeating and add it to an irrational? Still be irrational. So this one is I, and the next one's kind of tricky. Can you take a rational number and an irrational number, multiply them together, and get a rational number? So one example is 2 times pi, which is 2 pi. This is irrational. So if I take rational and irrational, I can create irrational. Can I take rational and irrational and get rational? There's one way to do it. I want something times pi that equals a number in Q. What's that? What'd you say? Go ahead. Be a big girl. What'd you say, Joseph? 0. That's the only way to do it. So this answer would be Q and I. So your assignment for the rest of the class and tonight is to go through and label the rest of those numbers. So you're going to label them as Q or I, unknown, or neither, depending on each problem. All right, get to work. Good.